How a single engine powers an entire aircraft carrier. Imagine a floating city as long as the Empire State Building is tall, carrying over 5,000 crew members, dozens of fighter jets, radar systems, and enough supplies to stay at sea for months. This isn't a science fiction spaceship, it's a modern aircraft carrier. One of the most fascinating aspects of these massive ships is how they are powered. Believe it or not, many aircraft carriers operate on the energy produced by a single engine system, specifically a nuclear reactor. But how does this one engine manage to power an entire city on water? Let's start by understanding what kind of engine powers these ships. Unlike cars or airplanes that rely on fuel-burning engines, most modern U.S. aircraft carriers, such as those in the Nimitz class, are powered by nuclear reactors. Specifically, 2 nuclear fission reactors, but each one is capable of powering the ship on its own if needed. These nuclear engines don't burn fuel in the traditional sense. Instead, they split atoms, typically uranium, in a process called nuclear fission, which releases an enormous amount of heat energy. This heat is used to boil water, creating steam. The high-pressure steam spins massive turbines, which are connected to the ship's propellers, generating thrust that moves the carrier through the ocean. But the same steam also spins electrical generators, producing power for the entire ship, including lighting, radar systems, computers, life support, aircraft elevators, and even desalination systems that turn seawater into drinking water. To give you a better picture, one reactor produces about 550 megawatts of power. That's enough to power a small city. And because it uses nuclear fuel, it doesn't need refueling for about 20 to 25 years. Compare that to a regular ship that needs to refuel every few thousand kilometers. A nuclear-powered aircraft carrier can stay at sea almost indefinitely, limited only by the crew's food and supplies. But how is this energy managed so precisely? A complex system of coolants, control rods, steam generators, and turbines is involved. Control rods absorb neutrons to control the speed of the nuclear reaction. If more power is needed, the rods are lifted slightly. If the ship is slowing down or needs less power, the rods are lowered. This ensures safety and efficiency, just like adjusting a gas pedal in a car. The energy doesn't just move the ship. It powers the catapults that launch fighter jets at incredible speeds. These catapults, on some carriers, are now electromagnetic, EMALs, which require huge bursts of electricity. The nuclear reactor easily handles this demand, something a traditional engine would struggle with. Moreover, nuclear-powered carriers support multiple aircraft hangars, repair facilities, kitchens serving thousands of meals a day, gyms, medical clinics, and advanced control rooms, all powered by the energy from a single engine system. It's a marvel of engineering that combines physics, chemistry, mechanics, and electronics into a seamless powerhouse. To make this even more impressive, consider the environmental benefits. Nuclear propulsion produces no greenhouse gas emissions during operation. It's also quieter than conventional engines, which is a tactical advantage in naval operations. Of course, managing a nuclear reactor is a serious responsibility. Specialized nuclear engineers and technicians are on board, trained to monitor and maintain the system 24/7. There are layers of safety protocols to prevent overheating, radiation leaks, or any kind of system failure. In conclusion, powering an entire aircraft carrier with a single engine system may seem unbelievable, but it's a reality. Through the use of nuclear technology, one engine, or technically 2 for backup and efficiency, supplies all the mechanical and electrical power needed for a city-sized ship to operate in the middle of the ocean for decades. It's one of the most powerful examples of how science and engineering work together to achieve extraordinary things. Like and subscribe.